Hello, and welcome to the latest lesson in the assessment series. This is part 4 on norm-referenced assessments. We're going to look first reviewing what that definition means for norm-referenced assessments. Then we will look at how we report norm-referenced results. And finally, we'll look at how to build a comparison table for those results before we discuss what's coming up in parts 5 through 9. So starting with our definition, a norm-referenced assessment reports student performance relative to other test takers, and not to some absolute external measure. Now, those test takers in some cases are a sample group that took the test prior to the current students. Sometimes it is the students themselves that are doing it right now. There are a few different ways to report the results. Some of the most common ones include percentiles, normal curve equivalent or NCE, grade equivalence or GE, and scale score or SS. Percentiles refer to a student's relative position in the population of the class. So the number of students that the person of interest outperforms. Higher numbers are better. A percentile of 25% means that the student outperformed 1/4 of the population, even if that student correctly answered 50% of the questions on the test. So percentile and percentage can be two very different numbers. A percentile of 50% means that the student scored exactly average, whatever average may be. And the intervals vary. So gaps in student scores do not necessarily create gaps in percentile scores. So if 100 students take a test and there are no marks in the 60s, then you can have a 1 percentile difference between 58 and 59, and also a 1 percentile difference between a score of 59 and a score of 70. Normal curve equivalent was created to adjust those percentiles, so that a gap of a given size in the normal curve equivalent results in a specific gap in skill levels in all respects. So that jump from 59 to 70 would be represented in the normal curve equivalent. So it's based on the Z-score from the bell curve. You can pull that from statistics, but it's essentially a measure of how far from average you are. And that distance from average is standardized according to the bell curve you're on, according to how much spread there is in the data. The formula for it is to take 50 plus 21.603 times your Z-score. Your Z-score is negative for below average scores and positive for above average scores. So this will put 50 in the center, and it will also balance it so that the first percentile and the 99th percentile produce NCEs of 1 and 99. So those are the 3 points where they match, 1, 50, and 99. But other than that, percentiles and normal curve equivalents do not need to match at all. They only do if the data in your data set is a very close fit to the normal bell curve anyway. A grade equivalent reports where an average student would be in their school career when they performed the same way as the student on the test. So a grade equivalent of 4.2 means performing like a typical student who's completed 2 months of grade 4, not all of grade 4 plus 2 additional months. It's easy to assume that 4.0 means finishing all of grade 4, that's starting grade 4, and the reason the curve was chosen that way was to accommodate kindergarten students as grade 0. So if you finish 2 months of kindergarten and you're performing exactly on average, your grade equivalent would be 0.2. And it's important to emphasize that it's not a grade level. An honors grade 9 math student might score 12.9 on a grade 5 test. So they'd score as well as a typical student who's in the last month of high school. That doesn't mean the grade 9 student is ready for calculus. That means they are making the same types and quantity of mistakes as the average student who's about to graduate. So you can have a student who performs at the grade 9 level on a grade 5 test, but at the grade 5 level on a grade 9 test. if they are a strong grade 7 student who has not been exposed to grade 8 and 9 skills. It's also not an equal ability scale. Students are expected to develop skills faster at older ages. So the amount of content you learn to move from 4.2 to 4.3 is not as much content as you need to learn to move from 12.2 to 12.3. 13.0 is typically the top of the scale, marking high school graduation. Now, a scale score is a way to build an equal ability scale. So two students who are 10 units apart have the same amount of skill gaps between them, regardless of whether those are 10 points at the grade 1 level or the grade 12 level. Unfortunately, there is no universal standard for what scale score to use. The test creators for each norm-referenced assessment can choose which scales they have. So this is the reporting method used by things like the SAT and the ACT College Readiness Test for the US. So they will give you a score out of 1600 for the SAT. That's the scale that they've chosen to use for the top end. So they decide, here's the maximum performance, here's the minimum performance, and then look at where the groups fall in between. Of course, before we can apply these scores, you have to come up with them. So the first thing you need is a large random sample of students. The only thing that they should have in common is the program of studies that they're working from. Ideally, they have different teachers, different school boards. So if you're teaching at a large university, you might have 500 students in your class. You can norm within the context of that class. That's how teachers mark on the curve. But that curve doesn't necessarily apply to another teacher's class. Different teachers will teach different topics at different levels of effectiveness. And ideally, the group should include all that the assessment is intended for and some others. So if you are looking to build a standardized grade 4 test, you should also include students in grade 3 and 5, if not 2 and 6 as well, to make sure you are getting a robust curve and you're getting solid data. And your sample population should be in the thousands in order to have strong enough statistics to really build a proper curve. So it's very difficult for a single teacher, even teaching multiple classrooms, to put this together, because most of us do not teach thousands of students. Now, when you're scoring it, you want to score the assessment for the entire population and then sort those papers by their results. So you have your sorted list with the top performers at one end and the bottom performers at the other. So to figure out percentiles, you have to figure out how far through that sorted list of scores do you need to go before finding this score. So you've got them sorted, in this case, from lowest to highest. You would start at the bottom, and if you have to go through 20% of the stack to get to that paper, then that's a 20th percentile. For the NCE, first you build the percentile scores, and you do it by filling out that statistical data to figure out your mean and standard deviation so you could calculate the Z-scores. And then you could correspond the grades to the given Z-scores. For the grade equivalents, once you've assessed students at all points in grade 4 or 3 or 5 for that grade 4 test we were talking about, then you could figure out, well, on average, how do students who are in the second grade of grade 4 perform? How are students who are in the third grade of grade 4 perform? And build your curve that way. And then finally, for the scale score, with that one, you choose in advance what the mean and standard deviation of these points are going to be. And then you build the scale score by matching the data to that curve. So if you decided the scale score is going to have a maximum score of 400 and an average score of 200, with, say, a standard deviation of 75, well, then you'd have your mean of 200 matches up with the mean score on the test. Your scale score of 75, you could compare that to the actual standard deviation on the test and build your curves that way. If you are not familiar with the statistics of how to build it with a Z-score, these lessons are not going to prepare you for that. That's a separate course on statistics. So in our upcoming lessons, Part 5 will look more deeply at criterion referenced reporting. Part 6 will dig into difficulty, discrimination, and bias. So instead of looking at overall test results, we will start looking at single questions and making sure those test or the assessment items are doing what they're intended to do. We will then take a look at parametric item response theory, which adds a whole layer of sophistication onto these. That parametric item response theory is the basis of computerized adaptive testing. And then finally, we'll take a look at non-parametric item response theory. And that will wrap up all 9 parts in this 9-part course.